Hello friends, welcome back to my channel. In this video, I am going to solve exercise question from book Topics in Algebra from chapter 4 Vector Spaces and Modules. Question is, if T is an isomorphism of vector space V onto W, prove that T maps basis of V onto a basis of W. Before proving the given result, we will recall definition of basis of a vector space. So, a subset B of a vector space V is called a basis of vector space V if B consists of linearly independent vectors and linear span of the set B is a vector space V. So, proof: here V and W are vector spaces over the same field F with T from V to W and isomorphism. Now note that since T is an isomorphism, so T will be 1-1 homomorphism. Now let us consider the set B consisting of vectors V1, V2 up to so on Vn as a basis of vector space V. Now since B is a basis of vector space V, the vectors V1, V2 up to so on Vn will span V. This thing come from the definition of basis of a vector space. Now let us consider TV1 equals to W1, TV2 equals to W2 up to so on TVn is equal to Wn. That is, the vectors W1, W2 up to so on Wn in vector space W are images of the basis vectors V1, V2 and Vn. Now first thing is to show that the vectors TV1, TV2 up to so on TVn spans image of isomorphism T. Now since T is an isomorphism, so image of isomorphism T will be W. So here we will show that the vectors TV1, TV2 up to so on TVn will span the vector space W. Now for this, consider any arbitrary vector, say W in vector space W. Now since T is an isomorphism, so T is onto, so there will exist a vector, say V in vector space V, such that T of V is equal to W. Now since V is any vector in vector space V, we can express V as a linear combination of basis vectors V1, V2 up to so on Vn in this way, where A1, A2 up to so on An are scalars coming from field F, and this representation is unique. Now we have W is equal to T of V. We can rewrite this as W is equal to T of A1 V1 plus A2 V2 plus and so on plus An Vn. We have just replaced this vector V by this linear combination. Now since T is a homomorphism, so this can be written as W is equal to A1 T of V1 plus A2 T of V2 plus and so on plus An T of Vn. Now here we can observe that W can be written as linear combination of vectors TV1, TV2 up to so on TVn, and so W will belong to span of vectors TV1, TV2 up to so on TVn. Now as W is any arbitrary vector of vector space W, so any arbitrary vector of vector space W can be written as or can be expressed as a linear span of vectors TV1, TV2 up to so on TVn, and therefore we can conclude that the linear span of vectors TV1, TV2 up to so on TVn is vector space W. Now next thing is to show that the vectors TV1, TV2 up to so on TVn are linearly independent. For this, consider the linear combination K1 TV1 plus K2 TV2 plus and so on plus K1 TVn is equal to 0 vector in vector space W. Now to show that the vector TV1, TV2 up to so on TVn are linearly independent, we need to show that the scalars K1, K2 up to so on Kn are 0. Now this can be written as T of K1 V1 plus K2 V2 plus and so on plus Kn Vn, since T is a homomorphism, which is equal to 0 vector in vector space W. Now from here we can conclude that the linear combination K1 V1 plus K2 V2 plus and so on plus Kn Vn belongs to kernel of homomorphism T. Now since T is an isomorphism, so T is injective, that is 1-1. So since T is injective, kernel of T will be singleton 0 vector in vector space W. And therefore this linear combination will be equal to the 0 vector of vector space W. Now we know that v1, v2 up to so on vn are basis vectors, so they are linearly independent. Now if we consider this linear combination is equal to 0 vector, so the scalars k1, k2 up to so on kn must be equal to 0. Now since this scalar comes out to be 0 and we have considered at first that this linear combination is equal to 0, so from definition of linearly independent vectors we can conclude that tv1, tv2 up to so on tvn are linearly independent. Now we have shown that vectors tv1, tv2 up to so on tvn spans the vector space W and also they are linearly independent. Therefore the set tv1 that is w1, tv2 equals to w2 up to so on tvn is equal to wn is a basis of vector space W from definition of basis, and therefore T maps the basis v1, v2 up to so on vn of vector space V onto the basis w1, w2 up to so on wn of vector space W, and this proves our result.